I am Bharathi, working as Associate Professor of Chemistry at Sri Sarada College for Women Autonomous, Salem 16, Tamil Nadu, India. Let us see about the charge transfer spectra. Before going in details about charge transfer spectra, we should know about the selection rule. There are two types of selection rules. One is spin selection rule, that is del S equal to 0. The second one is orbital selection rule or Laporte selection rule, that is del L is equal to plus or minus 1. The spin selection rule says that allowed transitions must involve the promotion of electrons without a change in their spin. The Laporte selection rule says that if the molecule has the center of symmetry, transitions within a given set of p or d orbitals are forbidden transition. That is, the allowed transition can only involves one electron excitation. That is, singlet to singlet, doublet to doublet, triplet to triplet are allowed transition. Singlet to triplet, doublet to quartet are forbidden transition. The spin selection rule for spin angular momentum is del S equal to 0. That is, spin multiplicity should not change during the transition. Thus, the transitions such as doublet S to doublet P and triplet D to triplet P are allowed, but transitions such as singlet S to triplet P is forbidden. The same selection rule is also stated that electronic transitions between the different states of spin multiplicity are forbidden. Let us see the examples. The first one is MnH2O 6 times 2 plus. H2O is a weak ligand. Mn in plus 2 oxidation state, that is D5 configuration. In this D5 configuration, all the 5 electrons are present in 5d orbitals. The S value is 5 by 2. It absorbs certain amount of energy and one of the electron is promoted in a parallel way to the higher energy state. This is Pauli's principle is not obeyed. That is S equal to 5 by 2, but spin selection rule is obeyed, but Pauli's exclusion principle is not obeyed. If the electron is paired in the higher energy state, the S value is 3 by 2. In this case, the change in S value from 5 by 2 to 3 by 2. So del S equal to 1, which is spin forbidden. The second case is COH2O 6 times 2 plus. In this CO in plus 2 oxidation state, which has D7 configuration, the S value is 3 by 2. By absorbing energy, one of the electron is promoted to the higher energy state without changing the spin. The S value is here, is 3 by 2. There is no change in S. So it is a spin allowed transition. The selection rule for total angular momentum J is del J is equal to 0 or plus or minus 1. The transitions such as doublet P 1 by 2 to doublet D 3 by 2 and doublet P 3 by 2 to doublet D 3 by 2 are allowed. but transitions such as p 1 by 2 to t 5 by 2 is forbidden since del j is equal to 2. Now, let us see about the Laporte allowed transition. Del L is equal to plus or minus 1. In this case, singlet S to singlet P and doublet D to doublet P are allowed. The Laporte forbidden transition is triplet D to triplet S is having the del L is equal to minus 2, which is forbidden one. The Laporte allowed transitions has a change in the parity occurs, that is S to P, P to D, and D to F. And Laporte forbidden transition, in this case, the parity remains unchanged, that is S to S, P to P, and D to D. In this case, the electronic transition within the same P to P or D to D subshells are forbidden. Hence, transition from gyrate to ungyrate and ungyrate to gyrate are allowed. Gyrate means evenness, ungyrate means unevenness. Gyrate means which possess center of symmetry, ungyrate means non-centrosymmetric. Now, U to U or G to G are forbidden one. Transitions which involves a change in L or del L is not equal to 0 are called Laporte allowed transition. Such transitions are very intense and have high absorbance. Transition which no change in the subsidiary quantum number, that is del L is equal to 0 or Laporte forbidden transition if the molecule has center of symmetry. In the centrosymmetric environment, transition between same orbitals such as S to S, P to P, D to D, or F to F transitions are forbidden since L remains the same or del L is equal to 0. S orbital, D orbital, G orbital have center of symmetry. P and F orbital which do not have center of symmetry. S to P, P to D, D to F are allowed transition. In this case, del L is equal to plus or minus 1. S to D, P to F, etc. are spin forbidden transition. In this case, del L is equal to plus or minus 2. S to S, P to P, D to D, F to F are forbidden transition. In this case, del L is equal to 0. There are two types of transitions. One is DD transition, another one is charge transfer transition. DD transition occurs in UV and visible region, but they are forbidden transition with low intensities. All transition within the D shell, such as T2G to EG, are Laporte forbidden because they are G to G transition. The intensity of the DD transitions that give D block metal ions colors are not very intense. The DD transition between same spin states typically have low molar absorptivities. That is, epsilon has 5 to 100. The same DD transition between states of different spin multiplicities have very low molar absorptivities. Types of transition. There are three types. One is spin forbidden, otherwise called a DD transition. The epsilon value is less than 1. Example is MnOH 6 times 2 plus. In this, OH is a weak ligand which has D5 configuration and also high spin state. So, It gives very, very pale pink in color due to deep P mixing. The Lepot forbidden, spin allowed in the second case. In this, epsilon value is 1 to 100, which will take place in octahedral complex which possess centrosymmetry. Example is TiH2O 6 times 3 plus. In this case, titanium in plus 3 oxidation state, which has D1 configuration. The another one is epsilon value is 1 to 100, which do not possess center of symmetry. Example is NiCl 4 times 2 minus, which is in tetrahedral form, which is more intense than octahedral form. The third one is charge transfer spectra. In this case, Lepot and spin allowed transition, which has the maximum epsilon value, that is 100 to 50,000. Examples are MnO4 minus, CrO4 2 minus. The charge transfer takes place either ligand to metal or metal to ligand. They are often extremely intense and are generally found in the UV, but in tail in the visible region. The CT transitions are quantum mechanically allowed, and as a result, in absorption bands with high molar absorptivity. An electronic transition involves electron transfer from one part of the complex to another. An absorption band is usually very strong, and they often produce rich colors, is called charge transfer spectra. In these electronic transitions, the electronic transitions are Lepot and spin allowed. A charge transfer transition may be regarded as an internal redox process. In this case, spin allowed as well as Lepot allowed. There are 4 types of charge transfer spectra. The first one is ligand to metal charge transfer or charge transfer to metal, that is CTTM. The second one is metal to ligand charge transfer or charge transfer to ligand, CTTL. The third one is metal to metal charge transfer or intervalence charge transfer. The last one is inter-ligand charge transfer or ligand to ligand charge transfer. As a general rule, the charge transfer will be metal to ligand if the metal is easily oxidized. That means metal loses its electron, so it becomes easily oxidized. Whereas the transfer will be ligand to metal if the metal is easily reduced. That means metal receive electrons, solely it is reduced. Therefore, it is not surprising that Cr in zero oxidation state in CrCO 6 times would have the electron density shifted from metal to ligand because chromium has D6 configuration, which possesses 6 electrons. In the case of Mn plus 7, in this, there is no electron in Mn, would have the electron density shifted from ligand to metal. Generally, donor is oxidized and acceptor is reduced. The electron transfer in ligand to metal charge transfer occurs when the ligand that is easily oxidized is bound to the metal center that is readily reduced. The second one is electron transfer in metal to ligand charge transfer occurs when the ligand that is easily reduced is bound to the metal center that is readily oxidized. Let us see about the ligand to metal charge transfer. Metals have empty orbitals in low energy state and also in higher oxidation state. Favors ligand to metal charge transfer transition. This type of transition occur if the following conditions are fulfilled. The first condition is the ligand should have lone pairs of electrons with relatively low energy and possess high energy transition such as S2 minus, O2 minus, Cl minus, Br minus, I minus, N3 minus, and OH minus. The second condition is the metal should have high oxidation state and must have low-lying empty orbitals. The examples are CrO4 2 minus, which has D0 configuration but orange in color. MnO4 minus, in this case also manganese in D0 configuration but very bright purple color. Likewise, HgI2, which is red in color, BiI3, orange red, PbI2, which is yellow in color, cadmium sulfide is yellow in color, lead chromate is also yellow in color. All are bright colors. Trends in MLCT energies. In this case of oxidation number +7, that is MnO4 minus is less than TCO4 minus is less than ReO4 minus. The energy of CrO4 2 minus is low when compared to MnO4 2 minus when compared to WO4 2 minus. In the case of oxidation number 5, for VO4 3 minus is less than NbO4 3 minus is less than TaO4 3 minus. The lowest energy transition takes place to the most easily reduced metal ions such as TaO4 3 minus, WO4 2 minus, and ReO4 minus. The second case is metal to ligand charge transfer. The metal is in low oxidation state, that means rich in electron, and a ligand possesses low-lying empty orbitals. Metal to ligand charge transfer occurs in empty pi star orbitals on the ligands become the acceptor levels in relatively high in energy. There are two conditions. The first one is ligand should have high energy empty pi star orbitals for cobalt containing CO 6 times, or carbonyls, cyanide ions, SCN minus, or NO. The second condition is the metal should have low oxidation state and must have high lying filled orbitals. Examples: Cn minus, SCN minus, carbon monoxide, pyridine, bipyridine, pyrazine, orthophenolphthalein, dithiolene, dithiocarbamate are the ligands which undergo metal to ligand charge transfer. The third case is metal to metal charge transfer, or IVCT or MMCT. In this case, metal to metal or intervalence charge transfer may define as the excitation and subsequent transfer of an electron from a low oxidation state cation to the neighboring cation of high oxidation state. That is Fe2 plus Ti4 plus gives Fe3 plus Ti3 plus. Fe2 plus to Fe3 plus, that is, it is oxidized. Ti4 plus to Ti3 plus, which is reduced. The best example is Prussian blue, which has bright, intense blue color, having the formula KFe, FeCN 6 times, owing to the transfer of electron from Fe2 plus to Fe3 plus. The other examples are Mn2CO 10 times, which is bright yellow, Re2Cl 8 times 2 minus, which is deep blue, CO2CO 8 times, which is purple black, MO2Cl 8 times 4 minus is cherry red, and Fe2CO 9 times, which is gold color, due to metal charge transfer. The last one is ligand to ligand charge transfer. The ligand to ligand charge transfer or interligand charge transfer may be defined as the excitation and subsequent transfer of an electron from one ligand orbital to the neighboring ligand orbital. A more specific form, ligand is reduced through metal ion to ligand oxidized complexes is mixed valence compound, which possesses the same ligand in two different redox states. Example, Cu TPASPH3. This is a rare one. Thank you.